morning, everyone. Today, I'm really honored to organize the TrustML Young Scientist Seminar and have our valuable guest, Professor Liu Yang from UCSC. I'm going to briefly introduce him to our audience, then he can proceed to his talk. Yang is currently an assistant professor of computer science and engineers at UC Santa Cruz. He was previously a postdoc at Harvard University, hosted by Professor Chen. He obtained his PhD degree from the Department of EECS, University of Michigan, Ann Arbor in 2015. He is interested in crowdsourcing, algorithmic fairness in machine learning. He is a recipient of NSF Career Award and NSF Fairness in AI Award. He has been selected to participate in several high-profile projects, including DARPA Score and IARP HFC. His research has been covered by media, including Wired, WSJ. His work on using machine learning to forecast future security incidents has been successfully commercialized and acquired by FICO. His recent works have won 4 Best Paper Awards at relevant workshops. Let's sincerely welcome Dr. Liu give his talk on the title of Matthew Effect when learning on weakly supervised data.
Thank you, Jingfeng, for the really nice introduction. Thank you again for coming to my talk. My name is Yang from UC Santa Cruz. And I didn't realize this is Europe's rebuttal week. So I hope everybody is enjoying the rebuttals and discussions. And I'm extremely honored and excited to talk about weakly supervised learning and Recon. We know Recon is a place for this topic, and I myself has been admiring a lot of results from Recon. And most recently, I had the fortune of working with Suge and Gang on relevant topics. So, my research interest was in crowdsourcing and machine learning, and naturally I look into the question of learning from noisy data and weakly supervised data. And also I work on this data bias issues, which is relevant to fairness questions. Today I'm going to talk about a not so traditional topic in weakly supervised learning, which is the observation we find in the past year or so that I summarized as the Matthew effect. Okay, so this is sort of a negative results that presents some warnings, but also opportunities. I'll be more formal when I'm defining this question, but quickly to put people into context, in case people haven't heard of it, the Matthew effects describe a really, really simple phenomena that is the rich get richer and the poor get poorer. Okay. And in the context of weakly supervised learning, I'm going to show you that for the data who has a richer presence in the population, they are going to benefit from all the solutions we developed. Okay, so they're really, really benefiting and becoming richer and they're going to enjoy higher performance. But for the data that happen rarely, or for the data that happen on the long tail, they're not going to enjoy as much benefits on the higher frequency data, and in sometimes the performance on this data may drop, so the poor will get poorer. Okay, again, I'll formalize this concept, but just to put people into this, just to explain this title. All right, and also as the title suggests, mostly I'm going to use this talk to formalize these observations. You can think about this is a negative results, or this is a finding. The papers I'm going to talk about do not really propose solutions. So we are not ready to solve this question yet. So if you ask me, how do we mitigate these Matthew effects? Towards the end of the talk, I'm going to give you some hints, but I think this question merits a more thorough studies. So if you're interested in this topic, I'm happy to chat. I think this is a really, really interesting technical question. All right. So we consider this like very classical classification task. So in the clean settings with supervised learning, you're going to be given a clean data set that comes in pairs of x, y. So x is the feature, that you're trying to learn with, and then the label Y is the thing you're going to predict. Okay. Again, in a clean case, each of the data is cleanly labeled with a label, so it's either class at 0 or 1. And for most of my presentation, or for easiness, I'm going to focus on binary classifications. Weakly supervision talks about the settings where the labels are imperfect. So either the labels are wrong or the labels are missing. For instance, in this now classical study of learning with noisy labels, you will be given a data set with this form of noisy labels. Like you have X, again, the features, comma, 1 tilde. And now the data are labeled as 0 and 1, but it's really, each of the class is really a mix of, true class 0 and false class zeros. Some labels are mislabeled by the labelers. The multiple ways this noise can be introduced, I guess, probably for part of this population, we all know this already, but I'm citing some of my group's work to highlight these possibilities. First of all, when you're getting the annotations from human, naturally, this human judgments can be noisy, either due to the difficulty levels of the task or due to the expertise levels of the human labelers. It can also come from, say, sensors. So we have a study to check out, to look into this weak supervision in reinforced learning. When you think about using sensors to sense the environments, there's a possibility the sensors went wrong. And in this case, your real-world signals will be noisy. So this is another form of weak supervisions. And thirdly, I'm highlighting with semi-supervised learning, there's a possibility where the supervisions are provided by models. And semi-supervised learning is one of the possibilities. And again, I'm not using, I'm pretty much missing a lot of references here, but I'm highlighting this paper that I'm going to introduce in this talk. All right. And the literature has been preparing a lot of solutions. Okay, so noisy labels, even robust reinforced learning, as well as semi-supervised learning. There has been a huge literature for each of the topics here. For instance, for learning with noise label, we know there has been a pretty rough package of solutions that have been developed in the past 10 years. Arguably starting from Narajan's paper at NeurIPS in 2013. But I'm categorizing some of the solutions here. We have developed sample selection approaches to extract confidence examples from this noisy data. I believe co-teaching is actually a recent product. We have people have looked into designing robust loss functions to make sure they will be robust against outliers. Okay, and there's also a category of so-called label noise learning, which is focusing on developing statistically consistent algorithms to deal with noisy labels. Okay, so a lot of progresses that have been made, but including some our own. But one question I always had is when I was developing my solutions, when I was comparing my solution with others, I'm always curious about what really happens behind these comparisons. Okay, so most of the analysis, or most of the existing analysis, focus on the population level analysis. Okay, so you have this. I'm going to use this D to denote the global population. So you're trying to say like how my classifier performs on this population. Okay, and this is not probably this is not unfamiliar. In all these papers, you're going to see similar tables and or a rank list of different approaches. And pretty much like the average performance will be reported for this approach on the test data. My question is, when we're comparing these approaches, how do this weak supervision affect different subpopulations in the data? When we're comparing model A with model B, and when we claim model A is better than B, what are the causes of model A better than B? Is model A consistently better than B on all the data points, or actually model A becomes better, but then it was actually hurting some populations in the data? Okay. In other words, as compared to this population level analysis, I was interested in how do these solutions fare at the instance level. Again, to give you an example, when I'm looking at these two approaches, model A and model B, Jokel and CRUZ, actually CRUZ was from us. These two approaches, they differ by 0.2% of accuracies. Okay, in this average on this global world, on this overall test distribution. But I want to know how these two models differ at different subpopulations. Imagine I have a data set that corresponds to users of male and female, and potentially there's an imbalance between the male population and female population. I want to know which model is faring better for which population. Okay, so this is the main query, or this is the main motivation of the study. We really want to break this evaluation and break this analysis down to the subpopulation level or the instance level. And this is a slide that summarizes the main takeaway of this talk. So if you are going to remember one slide or one message from this talk, I'm hoping it's this slide. So we do observe the rich get richer and poor get poor behavior when we are applying weakly supervised learning approaches. In this figure, on the x-axis, I'm ordering all these features, axes. Think about these are the representations of the data, and on the y-axis, I'm plotting the frequencies. Okay? And on this left-hand side, these are the data with higher frequency. On the right-hand side, these are the data with smaller frequency. You can think about these are long tail instances. And we show that for these high frequency instances, they have a richer presence in the data. Of course, they're going to have higher impacts of the noise labels because when you're minimizing this population, these risk terms are just like more dominant. But this part of the data, they are easier to fix. They do benefit from existing solutions. So we show this both theoretically and empirically. On the other hand, for the long tail data, they have a poor presence. They don't really present in the training data as sufficiently as the higher frequency instances. And arguably, they have a smaller impact on noise labels because the population is not high enough. But these are actually the harder instances to fix. Okay, again, theoretically and empirically, we show existing solutions may often fail to improve over this part of the instances. So poor does get poor. Okay, and the rest of the talk is towards formalizing this argument and this observation. Again, as I said, there are different ways of looking into this weakly supervised learning questions. And I'm first going to give you a case study of semi-supervised learning. Okay, and the main results of this part has been published with iClear 2022. You can find the codes and papers online, I believe, very easily. Okay, so just to recap, what is semi-supervised learning? In this case, you have a partially labeled data set. So you have some X and Y. The given Y's are clean, so possibly clean. You have clean class 0, clean class 1, but potentially a majority of the rest of data sets are unlabeled. So some labels are missing. So in this case, these are data, these are mixed in a box. You don't really know the true label class for these data points. And the typical flow of SSL, I'm not speaking for everything, but a typical way of unifying the flow of SSL is as follows. It builds on a bootstrapping procedure. You're first going to rely on the label data to build a initial model. Okay, so this is before you apply any of this SSL tricks, and then you are going to use this initial model to assign pseudo labels to this unlabeled data set. Okay, so sort of you're trying to propagate this label information from the label data to these unlabeled ones, and now you're having a you're going to have a mixture of clean data, which was provided initially, and then a noisy set of data. It's noisy because the pseudo labels are noisy, unless this model is clean or unless this model is perfect. Okay, and then you're going to use this noisy data to improve the model training. Right, and this procedure can take iterations until convergence, but this is the basic idea of it. Okay, how do we do the pseudo label stuff? And one way, and I think one of the most recent and popular approach is to use augmentations. So this is one way to do it. You have unlabeled data here. You have the model's prediction on this unlabeled data, but there's no way to write the loss functions for it. There's no way to evaluate because you don't have the labels. But imagine now I can create multiple augmentations by flipping the images. And now you can use a model to predict or to provide pseudo labels for each of the augmentations. And then the goal is to make sure the model prediction on the original and label data is consistent with the pseudo labels. If you believe, all these augmentations are pointing to the same class. Okay. One particular instantiation of the approach is called mix match. I think this approach was gaining popularities over the past 2 years. So here is what the pseudo labels are, how the pseudo labels are generated, and how the pseudo labels are used. Okay. For the unlabeled data, we are creating k augmentations, and for each of them, we are classifying them into a distribution. So this is a prediction of the classes of this augmentation. And then we take the average of the predictions over multiple augmentations, and we do some sharpening. Okay. And this gives us the pseudo label. And once we have a pseudo label, we're going to put this into a consistency checking function. But basically, you can think about this just a loss function. Okay. Then in the training or in the SSL training, the loss can be decomposed into 2 parts. The first part is the loss is defined on the label data, but then the second part of the loss is based on how consistent the model's prediction on the unlabeled data as compared to the pseudo labels. Okay, and the typical way or standard evaluation of semi-supervised learning is to look at the average performance. Okay, so here I have I calculate the average performance before I deploy my SSL algorithm, and then after I deploy this one, I check my average performance calculated over the population. And then I claim, okay, so my performance got improved, and I'm claiming my method works. This is typically how things are evaluated in the literature. However, this is what we found with one figure to illustrate. If we look into different subpopulations of data, okay, and some population, they may have a poor performance as compared to the average performance. And some population of data may have a richer performance, meaning their performance is higher than the average performance before you apply SSL. I'm going to tell you the multiple reasons why this is the case, but there's some disparity. So there's some heterogeneity in the performance before you apply SSL. But now, after you apply semi-supervised learning, this difference might get reinforced. So what we observe in practice is that for the richer group, their average performance is almost surely increasing. Okay, and the higher your performance were, the more improvements we were expecting, what we were observing. And however, more concerning is that the poorer group, their performance may actually drop after you apply SSL. So this was a concern. We are developing solutions to make things better on this data, but it turns out we are only getting better by hurting some groups. Okay. This raises serious fairness concerns, but also opportunities. If we can detect this is really the case, we can potentially, even just naively removing the SSL part for this group, will be improving the performance overall. All right. So this is a real case study we did on CFAR10 data. We tested the mix match algorithms as I explained earlier. And CFAR10 is a 10-class classification, image classification task. And in this synthetic experiments, we do very simple divisions. So each class is a population. So we have 10 subpopulations in the studies. And in the standard CFAR data, we have 5,000 samples per class. We give a really limited data size of the labels for each of the data. So to really fully operate in a challenging semi-supervised learning settings. And here are the results we show on the right-hand side. The way to read this figure is that the x-axis shows the test accuracy for each of the 10 groups before we apply SSL. And then the y-axis shows the test accuracies after we apply mix match. Okay. And each of the node is corresponding to one of the 10 classes. And the dashed line is y equals x. If any points is close to this dashed line, it means the accuracy stays the same before and after you apply SSL. And really quickly, we say the distribution of data really follows a monotonic trend, meaning from the data points who has a richer test accuracy, who has higher test accuracy before SSL, they tend to get the improvements because the points are above this y equals x line, meaning their performance got improved after SSL. And pretty much you can observe for the data for the group with higher accuracy already, their improvement is more clear or is more. But on the other hand, at the corner, for these two groups who had a lower accuracy before SSL, their performance actually dropped. No, so these 2 points are below this dashed line y equals x, meaning their test accuracy dropped after you apply SSL. We started to look into this question, like why this is happening. And in the end, we identified that this is because the question is highly relevant to the noisy label learning questions. Because as I explained earlier, after you assign the pseudo labels to the data, effectively we are working with a data set that is with noisy labels. And for different populations, if before SSL, the model or the population is enjoying a better model or enjoying higher performance, this baseline model is going to provide higher quality data or higher quality label for these unlabeled instances. Okay, and then these higher quality labels will be better leveraged in SSL. So this will give you even higher performance after SSL. Okay, so that was kind of the initial discussion we had. And now I'm going to tell you how do we analyze this formally. Okay, so really the high level intuition or the big picture of this analysis is that we are trying to connect this analysis of semi-supervised learning with this so-called instance-dependent label noise settings. Okay, instance-dependent label noise is a rising paradigm for learning, for modeling label noise with real-world patterns. Basically, it tells you that this noise rate for different data really depends on the feature X itself. To capture, different data has different difficulties being labeled, so on and so forth. But this model perfectly fits our settings because some of the data we had is clean, so it has error 0 because these were given, but some other data they were only associated with the pseudo labels, but then the quality of the pseudo labels or the noise rate of the pseudo labels will depend on the baseline models we trained. So, and also I put the equation, I just reflect on this equation again. As I said, you can think about this consistency check is a loss function. And if I just like redenote the pseudo label with y tilde, effectively, we are adding a loss function for this unlabeled data using a noisy label. Okay, to us, this SSL loss is very similar to a loss function defined over this instance-dependent label noise. All right, so to recap the formulations, we think SSL is highly relevant to learning with noisy labels. And if we, sorry for the table, so if we denote pseudo labels as a noisy label y tilde, we are effectively having instance-dependent label noise, meaning the transitions of y tilde from the true label y can depend on the particular data instance X. Okay. I'm going to come back to this point later, but by this formulation, effectively we show that the solutions to label noise may be able to help with SSL. So I'll come back to this later. And in our analysis, we are trying to capture the classifier's performance by its expected error on this clean distribution D. Okay, so this classifier is returned by semi-supervised learning, and we are trying to analyze its expected error or its generalization error on this clean distribution. I'm sure there has been a lot of analysis of semi-supervised learning in the literature, but we are hoping to derive a error term, or we are hoping to derive this term to capture the pros and cons, or to capture the tensions of using SSL. So the pros of SSL is that we are introducing more data, so we can expect better convergence, smaller variance, and better generalization. So this is going to give us a better data dependency. But the cons of SSL, as I explained earlier, is that we are using a noisy machine label data to perform the training. So this will introduce bias. And potentially, I'm going to show you that this is also introducing disparities due to the baselines performing differently across different data. Okay. And I just want to mention that for simplicity, I'm sticking with a D to just make the notations friendly. But this is not this analysis is done for each subpopulation individually. So you can think about this D is one subpopulation or one group of data in the population. Okay. The main result in the paper is theorem 2. We show that with high probability, the error, the expected error of a classifier returned by SSL can be upper bounded by the 3 terms here. The first term is eta. This is capturing the noise rate of the baseline models. Okay. So as base is the baseline model you trained without using any SSL. So I'm going to give you the detailed formula for eta, but at this moment, think about when this baseline model performs better, this eta is smaller. And when this baseline model is worse, this eta is higher, it's noisier. The second quantity captures the sharpness of the pseudo labels or the sharpness of this classifier returned by SSL. You can think about, this is less relevant in the discussions because you can pretty much control the sharpness when you're providing the pseudo labels. The last quantity is relevant too. This is the data dependencies. Okay, so N here is the total number of data we introduced in semi-supervised learning. Okay, so how do we do this? I'm going to give you a really quick sketch of proof. The way we analyze this term is not mysterious. It's pretty much elementary derivations. We first decompose this error term into 2 terms. The first term captures the gap between the noisy evaluation and the clean evaluation. So we are subtracting this the classifier's performance on the noise data. So this D tilde capturing the noisy distribution that is supervised by the pseudo labels. And term 2 is just adding this term back. But also you can think about term 2 is capturing how this classifier is performing on the noisy distribution. But also because this classifier is trained on this noisy distribution, you can think about this is error of fitting on this noisy distribution. Okay. Term 1. So how do we bound this difference term 1? Again, very elementary. So here I'm just using the definitions of the error terms. I'm taking the integral over how often the classifier disagrees with the true label minus how often the classifier disagrees with the noisy labels. Okay, this is the first line. Second line, for binary classification, I'm just flipping this disagreements to agreements, so nothing really happens. It's the same thing. Third line, I'm just bounding the difference because each of the density term is positive, and I'm just like upper bounding this difference term by the absolute difference. So I'm adding the absolute function here, absolute value function here, but I'm counting both cases. So it's like half of each of these 2 cases above. The reason I'm separating in this way is because for binary variables, this is exactly the definition of total variations. So this is equal to the total variation defined over 2 indicator variables, like if the classifier agrees with the noise label or if the classifier agrees with the true label. So this is a total variational difference between these 2 distributions. And the reason I want to write in this way is because I want to drop the dependency of the classifier and to capture, to introduce a term that captures the noisiness of the data, and the total variation difference allows me to apply the data processing inequalities. Okay, this is saying the difference between these 2 introduced random variables is upper bounded by the inherent differences that is defined over the noisy labels and the true label distribution. And then from here, I'm writing the definition again. This is just capturing how noisy this pseudo label or this Y tilde is, because this captures the difference between how often this noisy label equals a particular class I as compared to the true posterior of the true label. And I'm denoting this difference as eta. So very straightforward, but to wrap up or to recap, we showed that for a given SSL classifier, the first term is upper bounded by a eta term, which is capturing the differences between the pseudo noisy labels and the clean labels. Again, if the pseudo label is cleaner, this difference is close to 0, or if the pseudo label is noisier, this difference is high. And already from this term, we see some disparities. If some population or some groups, they enjoy a better baseline models, they are going to have a smaller eta here. Okay, now almost guaranteed the first term in the SSL classifier is going to enjoy a smaller error term in this part. For the second term, again, we did a really simple trick. This is pretty classical. So we are trying to bound the first quantity here, but we added another term, which is the absolute optimal error that can be achieved on this noisy distribution. So this FSSL is the optimal classifier defined on the noisy distribution. So we subtract this term, but then we are adding this back on the next slide. Okay, so to bound this, the reason we do this is because this is also classical three-way derivations. We introduced our hat is the empirical risk as compared to the expected risk defined on the distribution. So we are introducing this like empirical risk, but we are subtracting or adding in the back in the derivations. But because our classifier is trained on the data, so it has a minimum empirical risk. So the first quantity, the first difference here is upper bounded by 0, but then the rest two are just capturing, these are the maximum deviation bound, capturing the differences between the expectations and the empirical data. Okay, so nothing really fancy here. I promise that we are adding this absolute minimum error here back, but it turns out it just depends on like how sharp this pseudo label is. I'm omitting the details. But again, this quantity also tells us there's disparities in among different distributions, because for some distribution with higher with larger number of data in the training, this quantity will be effectively smaller. You're going to enjoy a better convergence when you apply SSL, but for a smaller group with a smaller frequency, this quantity will be large. Okay. And to wrap up, we are adding this back, showing the theorems. I think to also wrap up my discussions, there are two major sources of disparities, impacts of SSL. The first one is this disparity due to the baseline models. Some populations, they enjoy a better baseline models. So this eta term is going to be smaller, meaning, whatever performance you were enjoying is going to be recaptured or is going to be memorized or reinforced by semi-supervised learning here. The second source of disparity is caused by data dependency. Again, as I showed at the very beginning, depends on the frequency of the data, this convergence can differ significantly. Okay. All right, so this is just like from the error bounds perspective, but more formally, how do we really evaluate the disparate impacts in semi-supervised learning? What is the proper metric to capture the differences between different groups? For one thing is to formalize the discussion again, but also for another thing, if we can think about a new metric to evaluate this disparate impacts, we can potentially incorporate this new metric into training a semi-supervised learning model. So in the paper, we thought we have gone through several iterations of looking at different metrics, but we thought one metric that really stands out as a promising option, which we call as the benefit ratio. Benefit ratio on the high level is capturing the normalized improvements of the test accuracy when you apply semi-supervised learning for each of the population. Okay. More formally, for one subpopulation P in the data, we define its beneficial ratio as the following. Okay. So in the numerator, I have two quantities here. The base P, this is the baseline accuracy before you apply SSL. So do not use any unlabeled data. Just use the labeled data, get a model. So this gives you the baseline accuracy. SSLP is the accuracy after you apply SSL. So sort of this numerator is telling you how much you are improving or how much you are getting worse by applying SSL. But now we are normalizing it by a second difference. The difference here is capturing the difference of what I call full P. This is like this is the counterfactual case. This is as if the full data set is cleanly labeled. Okay, so this is sort of the absolute best performance you can hope for this population. And again, I'm subtracting the baseline performance. Okay, So intuitively, this is telling me how much, as compared to this like counterfactual optimal case, how much you are improving on this population by applying SSL. In our paper, we have theoretical results, but this quantity is pretty hard to analyze with in a closed form for multiple reasons. Like typically for these errors, for these accuracies, we only have the upper bound analysis. We can argue the techniques, but it's often very hard to have the exact quantity here. But also this full P is very much counterfactual. We don't really know. We don't really have a fully labeled data set. So it's pretty hard to argue or to calculate this quantity. But instead, we are using a proxy. So the reason we call this proxy is because we're replacing each of the quantity by its upper bound, by its maximum values. So to be honest and to admit, honestly, so this proxy may be broken because it's not even upper bound. By replacing each of the term to upper bound, it's hard to say whether the proxy is bounding the true values in which direction. Especially there's a subtracting and then there's a division. But empirically, we show this ratio has been serving the purpose, and also as I'm going to show on the next slide, it gives us some insight that explains this massive effect in semi-supervised learning. Okay. Particularly in our paper, we have a theorem that tells us this proxy, if we relax everything to the upper bound, has the following really, really clean format. Okay, so it's 1 minus eta divided by delta. So again, eta is not unfamiliar. So this eta captures the baseline errors. This delta captures the improvements in data dependency. So this is like how much of the convergence you're having before you apply SSL. So this n base is like how many baseline label data you had, and this NP is the entire data, including labeled and unlabeled data you have. So this the larger the difference is, the more improvements you got in the data dependency. Okay, and now let's look at this quantity. For the richer group, as I explained earlier, this eta term is smaller because the baseline model performs better on this on this richer group, and this delta is larger because these are the group with a much higher number of data. So the improvements in data is also significant. But if this is the case, you're dividing a small number with a larger one. So this quantity will be approaching 0. So this whole benefit ratio is going to approach 1, means SSL is fully extracting the benefits as compared to the counterfactual optimal case. But for the poor group, this eta is large because the baseline model was not accurate in supervising the pseudo labels. And on the other hand, this delta, this improvements in data is also low or moderate because this like poor group, they don't really have a lot of observations in the training. So now you're dividing a larger term by a smaller quantity, and this quantity may go even higher than 1. And now you're using 1 to subtract it. This quantity may be negative, meaning you're experiencing a negative benefit. So this group is becoming poor. Okay. And I think I showed some empirical results on mixed match earlier. This is another semi-supervised learning approach, which is called UDA. And again, we observe very similar performance using the benefit ratio. So here, again, in CFR 10, we are giving 50 label data for each of the 10 subpopulations. Each of the dot here is representing one of the 10 groups here. Okay, and again, on the x-axis, these are the accuracies before you apply SSL. So this is baseline accuracies, and on the y-axis, we're plotting the benefit ratio. So clearly, this line is a regression. This is the best linear fit of these dots, but clearly this line is monotonically increasing. Means for the group with higher baseline accuracies before you apply SSL, they enjoyed a much higher benefit ratio. All right, and for the people for the data with a lower baseline accuracy, the benefit ratio is arguably much lower. Okay, And one interesting comment when I was presenting these results earlier was that, these experiments seem to be very synthetic because these labels are used to separate the population, but in reality, there's a possibility these these subpopulations are hidden in each of the label class. You don't really know the membership of these populations. Just to make sure our experiments are not affected by knowing the group membership, we did another experiment to consider the subpopulations are implicit in the data. We don't really know, which are these populations, or this membership is not really used in the training. So to test this, again, we're switching back to mixed match, and we're using C400 to do these experiments because it's a good fit. Even though C400 has 100 classes, but these 100 classes are actually grouped into 20 meta classes. And then for each of the meta class, there are 5 final degree classes defined. So we are leveraging this structure of the labels. We're training with this 20 course labels. There are 20 meta classes, but we're treating the 5 final degree labels as a hidden or as an implicit subpopulations. So altogether, we have 100 groups. Okay, so everything else is pretty much similar. There's some differences like in how many labels we supervised. We tried different settings. We have similar observations, but again, on the right-hand side, we see a very monotonic trend. Again, the x-axis shows the accuracy before we apply SSL, and then the y-accuracy shows the benefit ratio. Okay, so rich get richer. The groups with higher baseline accuracies, they have a higher benefit ratio. But if you look at the corner here, there are some runs with experiments that return us a negative benefit ratio. Means some groups actually got a worse performance as compared to the baseline accuracy they were enjoying. Okay, so I'm going to briefly talk about another aspects, like what if we are handling the noise labels explicitly by using these approaches. But I'll stop here for some seconds in case there's a question. All right. So if there's no question, really quickly about the other things we checked. This is a paper we published at SML 2021 last year. The question is that, again, I'm re-showing the slide. We talk about the solution to label noise may help with SSL. Okay, so the previous study I showed you earlier, there wasn't a explicit step of correcting the label noise. So we are using the stool labels, we're using the noise labels directly in the training. But what if I'm using the loss corrections, or we are using other approaches to correct the noise in the label? Are we still going to observe this matching effect? Okay. Unfortunately, the answer is yes. Okay, let me give you a really simple case study here. Consider this like really simple noise label settings. This is called the class-dependent label noise, meaning we are going to observe a noise label based on the true labels. It depends on what the true label is. There's a certain chance of you observing the wrong label. So this for binary classification, this is captured by 2 parameters. But for multi-class classification, this noise model is captured by the so-called noise transition matrix. So you have the observational noise labels, the true labels are hidden, but then you have these transitions between noise label and true label. So this matrix is going to be, I'm going to denote this matrix as T. And one of the popular approach of solving or explicitly solving this label noise question is called loss corrections. The idea is pretty straightforward. We are going to use the transition matrix to correct the losses, because the losses you calculate on the noise label is introducing biases because of the transition here. So some of the losses are wrongly calculated, but now I'm using this T-inverse to correct these losses back to the hypostatic or the counterfactual true loss. Okay. The reason we can do this is because if you are calculating the expectation with respect to the noise randomness in the noisy label, this corrected loss in expectation is exactly equal to the true losses. Okay. So in other words, this corrected version of the loss function is an unbiased estimate, the true loss. And once this is true, okay, when you're performing empirical risk minimization on this, using this noisy, using this corrected loss of the noise label, the empirical risk is roughly converging or roughly equal to the clean risk defined on the, on the clean data, which you don't really know. So now let's look what happens. This is a theorem we proved in the paper that loss correction can fail on the tail data. So this theorem reads that for L frequent sample X, I'm going to explain what L frequent means with true label Y, with the substantial probabilities. So this is a probability that is bounded away from 0. Training using loss correction is actually giving you a higher generalization error as compared to doing nothing. Okay, so that is to say, for the data on the long tail with lower frequency, imagine this L is really, really low, with high probability, applying loss correction is actually giving you a worse model for this data. Okay? So this L frequent is a notion we introduced in the paper to capture the popularity of the instance. For example, if I call it data 10 frequent, you can think about this 10 images are capturing similar cats. Okay, so this similar patterns appeared 10 times in the data, and I'm going to call this group of instance as a 10 frequent sample X. Okay. Right, so we officially proved this, and also, unfortunately, this holds for other loss function too. This is not particularly true for loss corrections. This is also true for other loss functions that is developed for the noisy learning task. The proof is actually also substantially straightforward. So I'm based on 3 steps mainly. I'm gonna give you the sketch. The first step of the proof is to show that this T inverse, this loss correction, actually works, but under one condition. So this T inverse directs the model to the correct directions if and only if this empirical label distribution preserves the dominance of the true label. Okay, so what this means? That means the empirical label distribution does not need to be either 0 or 1. So it does not need to be fully agreeing with the true label, but it has to preserve the dominance of the true label, meaning the empirical frequency of this noise label equal to the true label has to be higher than all the other label classes. Okay, so if this is true, loss correction is going to direct the model to the right directions. However, step 2, we show for data that is on the long tail that happens rarely, with substantial probability, this condition is going to be violated. Meaning we can always find another class K that is not the true class, which is going to enjoy a higher empirical probability or empirical distribution as compared to the true label. Right. So combining these 2 steps, basically we showed this negative results. And one note I want to give is that this argument is even true with the perfect knowledge of the T, this transition matrix. There's a whole other discussion of how do you estimate this T perfectly. But one thing that really confused me earlier was that even in the control setting that I know the true transition matrix T, and even if I plug in the true transition matrix T, I didn't really observe the sort of the performance improvements as expected. Okay. Even though the T is clean, ideally you should be correcting the losses to the right ones, but empirically we do not observe the full potential being achieved by performing this loss correction. I think this result and this proof partially explain why even a clean T does not really give you the full performance improvements. This is because the imbalanced distribution of data. So I think with the remaining time, even though I said we didn't really focus on solving this question, or I didn't really focus on mitigating these massive effects. But in our paper, we did try easy things that we can do. So this is a case study. Again, we're using semi-supervised learning and the mixed text. This is sort of the mix match for the for NLP for a text classification task. So the idea is really simple. We had And I think in the literature we talk about in domain adaptations or in even in noise labels, we talk about balancing or reweighting the data. I think Sugi has contributed to this literature significantly. So we tested this really simple idea. When we have different distributions of populations, we can just balance this data by reweighting the minority groups, right? If you have a smaller presence, I'm just going to assign higher weights to this data. And we also tried to balance both the labeled data as well as the unlabeled data. And we also tried to balance both labeled data, unlabeled data, but also to collect more data. Okay. And so in this experiment I'm presenting right now, this is the battery classification question on Jigsaw. So classifying whether a sentence contains toxic comments or not. So it's either toxic or non-toxic. Okay. And we're breaking the evaluations into different racial groups, like for Asians, Black, Latin, and white, 4 different groups. So this table is recording the benefit ratio. Okay, and probably you don't really need to focus on this one, except for that, the entries highlighted in red color, these are indicating the negative benefit ratios, meaning these are groups who suffered from applying this semi-supervised learning approach. And the column I want to highlight is this last one. This is standard deviation. If this quantity is higher, meaning there's a higher difference across different groups. If this quantity is lower, meaning sort of the difference is smaller, and we were able to mitigate the differences between different groups. So we do observe that by keep balancing the data, as we discussed earlier, we were able to consistently reduce the standard deviation across different groups, meaning different groups are enjoying similar benefit ratios. But also we are removing the negative entries. So we are making sure more and more groups are enjoying from this semi-supervised learning approach. Okay, but again, as I said, I think this is a really simple trial, and I do encourage people to think about evaluating weakly supervised learning from this sort of new perspective. Right. To summarize this talk, the main takeaway is that there exist massive effects for weakly supervised learning. We show this both theoretically and empirically. And we do think developing trustworthy semi-supervised learning algorithms or weakly supervised learning algorithms requires rethinking the objective functions. Okay, so we need to go beyond looking at the global or the average accuracies across population, but rather we need to look at this, subpopulation or even instance level performance of the model. And as I said, I think disparate impacts or the massive effects present some warnings. This is showing we didn't fully solve this weakly supervised learning question at this moment, but also these papers told us that there are opportunities, right? So if we were able to tell people, or if we are able to show people, these are the populations who didn't enjoy the improvements, or these are the populations who actually became worse by applying semi-supervised learning, we can potentially try to focus on these groups and develop solutions to make them perform better. And this opens up new opportunities and new possibilities to further improve the weakly supervised learning solutions. Okay, so with this comment, I'm stopping here, and I'll be happy to take questions. And if people have comments or anything, I'll be happy to take.
Thanks, Yang, for a great talk. Hi, audience. If you have any question, you can open your mic directly to ask. Before that, I gonna have a question. Ask for Yang. What your theory? How your theory connect to the no free lunch theorem? Yeah.
So, I guess like there are different versions of no free lunch theorems. Like which one or which context are you referring to? Kind
of like in general. I'm thinking about no-free lunch theorem basically here, the no single algorithm can handle all possibility of data set.
Right.
Yeah.
So I think definitely there's a connection to the no free lunch theorems. But I wouldn't say this is exactly the same thing, because we do have, for instance, like this scenario. This scenario, even though there's a disparate improvements, but still, like, all the benefit ratios are positive, meaning like every single groups, as long as you have sufficient model data, they are all improving. So I guess this is a weaker version of no free lunch. You're hurting some groups, or you're not improving for some groups sufficiently, but overall you're still improving. So I wouldn't exactly attribute this observation to no free lunch theorems for semi-supervised learning. So for many cases, we actually observe SSL actually works pretty well.
I see. Okay, got it. Thank you very much.
Yeah, that's a great point.
Another question coming up. You can look at the chat box. Sorry.
Yeah. So I got another question in the chat. Is from Yashong Liu. Could you please emphasize why the rich guy richer principle in the slide will not lead to overfitting? Yeah, so I guess the rich guy richer phenomena is not going to give us overfitting. I guess the part of the reason is that let me show this one. My take of this question is that there's independence between the label data and unlabeled data. Okay, so we are using this label data to provide pseudo labels, or to provide some information for the unlabeled data, and because this baseline model is trained on a different data sets, so it's providing some, theoretically speaking, it's providing some independent information for the unlabeled data. So that's why we are expecting some performance instead of overfitting. But this is only based on the assumption that this baseline model is accurate enough. So in other words, possibly if the baseline model is not really performing well, or if this baseline model is overlapping with unlabeled data, we do observe some overfittings. In this case, the model performance or generalization error actually start to drop. A parallel comment to this question is that our analysis probably there's a disconnection. So our analysis probably does not fully apply to super deep neural nets, because this generalization bound, I think there's some questions about how generalization bounds holds for deep learning. Seems like models can super deep learning models can memorize the training data entirely, but the generalization power can be a different story. So to admit, our analysis is built on the classical generalization error case. It's not really touching on the overfitting behavior of deep learning. But this is a great question.
Okay.
All right.
Yeah.
If there's no other question, this
Sure.
is my email. So if you want to follow up with other questions, feel free to do so.
Sure. Thanks again for Dr. Liu's great talk. This is the end of today's seminar. Thank you very much.
Thank you all. Yeah, hope to see you at the conferences soon.
Yes, hope to see you soon. Bye-bye.
Okay, bye guys.